Our first Extension 2 topic, we're going to delve into the world of complex numbers. Why is it useful? Well, the first reason is to solve quadratics. You see, we get something like this. X squared plus 1 equals 0. Very simple equation. X squared equals minus 1. And up until now, we'd say, well, there's no solutions. Well, in reality, what we should be saying is there's no real solutions. You see, we do this in maths. We sort of lie to you and say there's no solutions. And then later on we go, well, actually there is. You know, it's like, think back into primary school when they said, what's 3 divided by 4? And you went, nah, 4 doesn't go into 3. Can't do it. And at that point, that was your answer. But then we learn about fractions and then you could do it. You know, what's 8 minus 10? Can't do that. 10's bigger than 8. Then we learn about negative numbers, and that allowed us to do it. So it's the same thing here. At this stage, we're saying, can't do it. So what we do in maths, whenever we can't do something, we create a new number so that we can do it. And this is our new number. It's simply defined to be the square root of negative 1. Okay, we don't know what it is. So we just call it, that is the Greek letter iota. So it's the Greek letter iota, which we often use for numbers we don't know the exact value of. Well, in pi being a classic example, we use the Greek letter pi to represent that. E we've looked at. Well, E is not a Greek letter, but we use a letter to represent this number we don't know what it is. And it's the same here. Don't know what I is. But if we just understand it to be the answer to the square root of negative 1, whatever that happens to be, that then allows us to progress with our maths and solve more problems. Because now I can say, well, x squared equals negative 1, so x would be plus or minus the square root of negative 1, and we know the answer to that is, well, I, which really is iota. Mind you, we do tend to say I because it's quicker. So the actual definition is probably I squared equals negative 1. That's probably more correct. But I mean, obviously they're the same thing. So let's define how we write down complex numbers. X plus iy, so any complex number z, x plus iy, where they have a real part and an imaginary part. See, x is representing the real part, and y is representing the imaginary part. And it's a really bad word that we use, imaginary. Because by using the word imaginary, people all of a sudden are under the belief, oh, it doesn't exist. It does exist, but for some reason we decided to call them imaginary numbers. Just like we called negative numbers, negative numbers. It's just a name. They do exist. They're not fictitious just because we're using the word imaginary. So if I have 3 plus 5i, the real part is 3. The imaginary part is just 5. It's not 5i. The I is telling us that's the imaginary part. So the size of the imaginary part is 5. Now if the real part happens to be 0, then z is an imaginary number. You probably hear the term more often, not just imaginary number, but a purely imaginary number. So it has no real part. Some examples, root 3i, minus 6i. In fact, I could throw any number I like in front of I, and it's going to be a pure imaginary number. Well, if the imaginary part is equal to 0, and that's what we've been used to dealing with so far, where there's been no imaginary part, then z is a real number. Some examples of real numbers. 3/4, pi, e, negative 4. Every complex number has a complex conjugate. We've seen that word before, conjugate. Where have we seen it? Surd. Well, think about it. I is a surd. It's the square root of negative 1. So it has similar sort of words. So it's symbolised with a bar over the top of z. And we just change the surds to the other sign. So the imaginary part. So x minus iy. So if we've got minus 2 minus root 7i, its conjugate would be minus 2 plus root 7i. Okay, let's have a look then at our numbers. So far we've been dealing with just real numbers. Real numbers, a simple definition is any number that you can place on the number line, which is why it's sometimes called the real number line. Symbolised R, but notice it's the hollow R, it's not just an R. Then inside the real numbers, we got rational numbers. Symbolised Q, Q standing for quotient, because the rational numbers are all the ones that we can divide nicely. we can get a quotient. The other family then is irrational numbers. There's not actually a symbol for irrational numbers. That's one way of doing it. R\Q. The backslash just means not including. So it's the real numbers not including the rational numbers. Therefore, we must be left with the irrational numbers. So inside the rational numbers, we have fractions. And by fractions, that's what I mean. Anything that can't be simplified to be a whole number. So 4/1, I'm not considering a fraction because it could just be 4. 4/1, in fact, would be in the integers. Symbolize Z because Zahlen is the German word for integer. And so that's why we get Z for integers. Inside the integers, we have the natural numbers, symbolized N. Natural numbers, also known as counting numbers, cardinal numbers, I think, another name for it. But basically they're your positive integers, 1, 2, 3, 4, 5, so on. Then we have that really weird number, 0. Sort of sits in a set all by itself. But then overlying all those, we have the negatives. So you can have negative irrational numbers, you can have negative fractions, you can have negative integers, but notice it doesn't overlap the naturals or 0, because you don't have negative natural numbers and you don't have negative 0. They're all the numbers we've been working with so far. But now we can actually place that whole set inside another one called the complex numbers. So you have been dealing with complex numbers all your life. It's just a type of complex number. Complex number, symbolise C. Real numbers, that's when the imaginary part is equal to 0, that's what we said. But now we have this other set over here. Imaginary numbers, they're pure imaginary numbers, they're the ones where x equals 0. And of course there'd be other numbers outside that, but still inside the complex number ones where you got a real part and an imaginary part. We can't really break down the imaginary numbers into anything else because you can't order an imaginary number. You can't say this one's bigger than the other one. You can only order something that can be placed on the number line. Well, that's the real numbers. How do we deal with them then? Good news is you already know. I is a third. So all those rules about surds, well, they're the rules for dealing with complex numbers. So addition, if I had to do this, you could also think of it like algebra, really. We get -4 minus I. You see, there was no point of intersection of the real numbers and the imaginary numbers. There is no point of intersection. So you can't add them together. So you always have a real part and an imaginary part. You work with the imaginaries, you work with the real numbers. So -4 minus I is the best we can do. So subtraction, same deal. Again, just looks like algebra. Multiplication, well, looks like one of our binomial products. The difference is now that we don't leave it as 6i squared. Remember, I squared is defined to be -1. So that minus 6i squared is actually plus 6. You don't normally write down the minus 6i squared. After a while, you'll get used to looking at it and going, oh, well, that's 6. In fact, you could probably look at it with the minus 32 and go straight to minus 26 plus 32i. Division is what we call realising the denominator. With surds, it was called rationalising the denominator, but it's the same thing. So I would multiply by the conjugate. So minus 8 minus 2i on minus 8 minus 2i. So top of the fraction, expand that out. Bottom of the fraction, difference of 2 squares, but of course it becomes the sum of 2 squares because of the I squared. So on the bottom I get 64 plus 4. And there's my answer, minus 19 on 34 plus 8 on 34i. So all things we already know how to do. The only thing we've got to be careful with is that I squared is -1. Some basics about how we play with conjugates, how we deal with them. The order that you do things in does not matter. So you could add the two numbers together first, then find the conjugate, or you could find the conjugate of each number and then add them together. Doesn't matter. Same with multiplication. You could multiply them first, then find the conjugate, or find the conjugates first, then multiply them. Division, same thing applies. Now z times z conjugate, that was the one we just saw when we were realising the denominator, right? Becomes the sum of 2 squares. So it's the real part squared plus the imaginary part squared. If you want to find the reciprocal of a complex number then, you'll always end up with the conjugate over x squared plus y squared, because you'd be multiplying top and bottom by the conjugate. So if I want to find the reciprocal of 4 minus 3i, Well, it's 4 plus 3i on the top, the conjugate, and on the bottom, sum of two squares. So 16 plus 9. So 4 25ths plus 3 25ths I. Equations then. You can't mix your real and imaginary. So it's a bit like, quadratic identities when you said, the coefficient of x squared must equal the coefficient of x squared. Same idea here. The real part must equal the real part. The imaginary part must equal the imaginary part. So if you've got two complex numbers like this, the only possibility is that, well, A1 must equal A2 and B1 must equal B2. Real part equals the real part, imaginary part equals the imaginary part. So something like this. There are different ways I could do it. I mean, I could divide both sides by 2 plus 3i. That would work. Or I'm going to go the long way about it here. On the left-hand side, I've actually expanded out. I group the real and imaginary and go real equals real, imaginary equals imaginary. So real on the left-hand side, I've got 2x minus 3y, so it must equal 4. And imaginary, I've got 2y plus 3x, that must equal negative 2. I just solve those now simultaneously. And eventually, there we go, x is 2/13, so y would end up being 16/13. Simultaneous equations involving complex numbers. But again, the rules don't change. So how would I approach something like this? Well, I want the coefficient of z or the coefficient of w to be the same. So I'm going to make them both 2iw. That means the second equation there, I've multiplied by 2. Okay, I can eliminate the 2iw. I get 3z is 2 plus 5i. There's z. Substitute back in, I can now find w. So move that to the other side. Divide by 2i. You never leave the imaginary part in the denominator. That's where it is different to surds. Like, we're okay with surds to leave the root on the bottom. For instance, what's the tan of 30 degrees? 1 on root 3. We're happy to leave it like that. When we're dealing with imaginary numbers, we don't leave it in the denominator. So I've made mine 2/3 minus 5/3 I. Time to play with complex numbers. Exciting.